Good evening, everyone. Welcome to the session on UAV code generation and deployment with MATLAB and Simulink. So in the previous session, we talked about how can we do the flight simulation. Mostly we talked about the open loop flight simulation. How can you connect an RC controller? How do you model environment? How do you model a plant model, your vehicle itself? And how do we do finally the flight visualization? So mostly we talked in the previous session about the open loop flight simulation. Now the idea is to move forward from open loop flight simulation to autonomous flight simulations. So all the autonomous flight vehicles take some type of code or some type of algorithm which helps them to become autonomous and perform certain missions. So if for your competition, if you're working on something which required following waypoints or avoiding an obstacle in your mission, then this webinar content may be directly useful for you. And as the Aerothon competition problem statement is similar, so today in this webinar, in this workshop, we are going to talk about how can you use MATLAB and Simulink for generating your code, especially for the hardwares like PX4 autopilot hardware and Raspberry Pi and NVIDIA Jetson flight computers. So let's quickly move forward and see what all are we going to have in this section. So before we learn about the nitty-gritty use of the hardware in the loop simulation or the software in the loop flight simulation, we'll talk about how do we prepare overall virtual environment for these simulations, and how do we test the generated UAV code. So before even generating UAV code, we have the vehicle modeling and simulation. So how each of the part fit where in the frame, and how does each of them interact with each other. Moving forward, we are going to talk about the PX4 best autopilots. So how do you generate the code for them? And how do you deploy these codes to the Pixel autopilots? Moving forward, we'll also talk about code generation and deployment to the flight computers, which are mostly either the Raspberry Pi or Jetson that we have witnessed in previous years of Marathon. So we are going to also talk about deployment to these hardwares. And finally, we'll wrap up this session with some of the learning resources. Yes, this session is going to be a bit long. It's more than an hour session, but don't worry, we are going to have some breaks in between so that we learn a lot of we learn, and we also take some rest, and we make the best use of your time. So let's start our journey with understanding with preparing virtual environment for UAV code. Uh, Before I get into the details, can you let me know in the chat that what do you think, why this virtual environment preparation is important? Why can't we just directly do the simulation the way we previously did? Or what are the special points that we should take care while doing such type of simulations? Please feel free to let me know in the chat, or feel free to turn on your mic and speak about it. Virtual environment. Why do we need a virtual environment? Everything we are doing in simulation, everything is virtual environment, right? But what are the various subsystems or various platforms which we need to use and accordingly perform the simulation? So let's move forward and see how do we fly an UAV. Let's learn from a simple manual flight and see that how can we bring the manual flight requirements into the virtual environment. So consider an UAV that your pilot is flying in your competition, and it's a manual competition. So first requirement is, if we want to have an easier flight, we use the Pixel-based flight control hardware, which makes the pilots work easier. So consider your drone or your UAV or unmanned aerial system is equipped with this autopilot hardware. Next thing we need is we want to visualize that how our vehicle would be flying in the virtual environment. So we need the scenario simulation. In the previous webinar, previous workshop, we talked about how do we do the such scenario simulation, flight simulations with Simulink, and how can we do the custom flight simulations. And we also talked about the flight modeling, flight vehicle modeling and environment modeling in these cases. So once you do the scenario simulation, the next step is replacing your own vehicle. So you can, instead of putting your hardware, physical vehicle, you can replace your vehicle with plant modeling. That's what in the previous workshop we were calling the aircraft dynamics. Here, in the case of rotorcrafts, it would be rotorcraft dynamics. But the vehicle modeling or plant modeling is required. Once this plant modeling or vehicle modeling is required, maybe for the autonomous system when we are working, we want to replace the pilot as well, and we want to perform the mission with a ground control station. So we need to use some type of ground control station. It can be the Q ground control or mission planner, which actually plays a role of the ground control station. Now, as we have all of these parts, the idea is how these platforms interact with each other. We see that one is QGC ground control station, another one is in Simulink, and another one is Unreal Engine based visualization. So how do they interact with each other? And moreover, if you have a PX4 based or Autopilot based autopilot, how do you test the code of autopilot hardware in such an environment? For example, I do have this PX4 Cube Orange Plus autopilot connected to my system, and I deploy some code, some controller code or some algorithm on this hardware. Then how do we estimate or how do we test that this autopilot algorithm is working in correct way? The ultimate goal of performing the simulations is to test that the algorithm we design are giving us the adequate performance or desired performance or not. And accordingly, we design our flight controller or tune it. So for all these purposes, we need to have some type of connectivity system among all of these subsystems. So for this purpose, we use the first thing we use is Mavlink. So if you are aware about the Mavlink connectivity, it stands for Micro Aerial Vehicle Link Connectivity. So by this Mavlink, by creating the source and sink of the Mavlink bridge, we receive the data and we provide the data to the Mavlink. Now, with this Mavlink connectivity, we use the serial communication to connect our autopilot hardware, and with this autopilot hardware, we writes commands to our autopilot and also reads commands to this. Using UDP TCP communication protocol, we connect with our ground control station and the scenario simulations. So once all these things are in place, we can actually perform our hardware in the loop simulation or the software in the loop simulation perfectly. So right now, in this workshop, we are going to focus mainly on how do we bring these hardware and these subsystems together, and how do we perform this type of simulation. So let's move forward and understand which are the various parts that we already talked, and what are the new parts we are going to talk about. How are we going to generate and deploy the code on these hardwares? So let's move forward and talk about the code generation and deployment to the autopilot controllers. So before I get into this, how many of you are aware that you can, instead of writing the code, you can actually generate the code? Let me know if you are aware, say yes. If you're not aware, say no in the chat. We want to make this session as interactive as possible, so that we make the best use of the time and the demos we have. Aryan, not Harsh, Madhur, Path, Om. Okay, Madhu says he's aware about generation of the code. So Madhu, can you tell us that how do you do it? Maybe are you using some type of software for this or any type of templates do you have? How do you do? How do you generate this control code for the hardware? Okay, let's move forward and find the answer for this. How do we do it? So as we are going to talk about the autopilot, by the end of this section, our goal is to finally fly a mission with QGC and learn that how can we deploy the flight controller code on the hardware, and from a ground control station, how can we run this? How can we run these simulations? So you can see that here, the from takeoff point to the away point, your drone is going, uh, and how does it land? So let's move forward and assess it, that what is in the flight controller and what all do we get it. So before we get into it, we talked in the previous session about modeling and simulation of UAVs, and in the previous workshops video would be soon available on YouTube. But if you did not attended the session, you can check out our video on the flight simulation for aerospace design competition. We will share the content of this video, the link for this video after the session with you. Uh, so once this you are ready with the simulation, the next part is flight controller modeling and deployment to the autopilot hardwares. Mostly the teams are using the Pixoc hardwares, and so we will try to focus on the PX4 or PX4 best autopilots. So the flight controller modeling you can do in Simulink, and the idea is you do all the modeling in the Simulink, you tune your controller, and finally you generate the code and deploy it on hardware. So for such type of for this workflow, when we are doing efforts, most of the teams has asked me these questions in the Aerothon competition. All the autopilots comes with their default flight controllers. Why do we need to design our own flight controller? What is the motivation behind it? So let me know in the chat, what do you think? Why should we design our own flight controller? Isn't the flight controller coming with the out of the box hardware is not good enough? Or it's just for the fun you want to do it? Does industry design their own flight controller, or they just use the stock flight controller that comes with the hardware? If you want to find the answers of all of these, there is a video series is available on drone simulation and control. So you can go through this video series and learn about it, that why actually we need to design our own flight controller and how do we do it. But for today's session, we'll talk about this in this workshop. Once you design your flight controller in the Simulink, you can actually generate the code and deploy on the PX4 hardware. We are going to also talk about this during the session. But before before we move forward, I want to understand your motivation. Why will you do it? Or would you even considering designing your own flight controller or not? First, let me know if will you consider designing your own flight controller? Yes or no in the chat. More interactive the session, the more value we will bring out of this workshop. So Mitansh says that Mitansh Tanvi says they will design their flight controller. Good, but why do you want to do this effort? Is there any motivation for that? Madhur also says that they will design the flight controller, and I would love to know your motivation. If you have long answer and you're refraining to type in the chat, probably feel free to turn on, unmute yourself and speak about it. So Tanvi says that for making it cost effective and for self-learning. That's good. I like that, Tanvi, because as part of the Aerothon competition or any student competition, the projects you work on that gives you the learnings, the technical learnings you have are actually the skills you earned by with this competition and useful in the industry. So that actually helps you to become the more and more advanced in your field and increase your employability or increase your uh, own technical work chances. So Midans is saying we can customize controller according to our needs. Madhur is saying to optimize according to our use cases. Okay, let me put one more question here. Do you only need a flight controller design or do you need an algorithm for flight computer as well? There's a difference between flight controller and flight control computer. We'll be talking about both, but I want to hear from you that is it we should do for both? All of the answers that you gave are correct, that for your own mission, for your own vehicle, you should design a flight control. Consider a case of a vehicle, a custom vehicle you design. Depending on its weight, depending on the environment it's operating, and depending on the hardware it has. Along with that, how long has been this hardware or the motors or the propulsion system have been using, the performance of the vehicle actually changes. And to take care of all of these cases, we need the flight controller. We need our own custom flight controller. Also, there can be the possibility that the environment you are operating in, maybe it's a high wind environment or high altitude environment, where the stock flight controller is not actually suitable enough. And that's where the custom needs comes. Uh, it's not just that for Aerothon or for the student competitions you design flight controller. Even the NASA has designed their own flight controller for their multi-copter test flight. They performed the aggressive maneuvers and they developed their complete flight controller models in Simulink and deployed the controller. They could build accurate controller for customized vehicles uh, and deployed to the physical controllers. And that could actually help them to get to their vehicle mission, or say their vehicle objective of designing their vehicle uh, quickly. So before we get into this, that why should we develop, how do we design a flight controller? Um, I want to check with you. Are you guys excited to learn how do we design a flight controller, or what are the various parts of the flight controller? If you are excited to know, let me know in the chat in yes or no, because there is a big section for next 20 minutes. We are going to talk about the flight controller. If you want to learn about flight controller, type flight controller in the chat. You have 14 people in the chat. At least I expect 10 flight controllers in the chat before we move forward. So Mitans is interested, Tanvi is interested to learn about it. Madhur is interested. Anyone else? What about Om, Fireflies, Dikshit, Chris? Path is interested. Good enough. We have more people coming up. So yeah, we can move forward and learn about how should we design flight controller. But even before we learn about designing a flight controller, let's talk about some basics of drone motion. So we know that drone has 6 degrees of freedom, and it has motions like up and down motion, left and right motion, forward and backward motion, and then it has 3 rotations. These are about x-axis, it's called roll. About y-axis, it's pitch, and z-axis, it's yaw. So we see that we have 6 degrees of freedom, but when we want to control, we have only four, four motor propeller best propulsion system. So what we can actually control is thrust, pitch, yaw, and roll. So now the idea is, if we do have a thrust, pitch, roll, and yaw, our system is actually an under-actuated system, right? So 4 controllers are actually taking care of 6 motion. So how can we make that possible? So that was a very good engineering problem when the drones, when the UAVs, or especially the rotorcrafts, under-actuated system controls work started. So let's move on and see. I remember this slide we discussed in the previous session as well, but let's see. Let me ask you again about. Let me go through again about this. Consider a drone flying on some angle. It will generate the thrust because of its motors and propellers. So if we do the break of all the force component, we see that thrust is applying the for upwards and the weight is applying downwards. Now, if we break the forces, lift and drag forces would be there, and thrust has will also have a component which will result in the forward motion force. Now, depending on these force component contribution, we can make that pat is equal to thrust cos theta and drag is equal to thrust sin theta. Now, the question is, we have two cases. The two drones in the one configuration A, both the rotors are actually flying in the both the rotors are actually rotating in the same direction. In another one, they are rotating in opposite direction. What do you think? Which one is the correct approach? And what happens if we take the other one? The people who say is for who are in the favor of A, mention A in the chat. People who are in the favor of B, mention B in the chat. Mitans, it's saying B, which is counter-rotating propellers. Anyone in the favor of A? Think about it in this way. When your rotorcraft's propellers are rotating, based on their rotation, they will create a moment on your center of gravity. So this cross mark that you see is nothing but your center of gravity. So if both are rotating in the same direction, they will have a positive moment on the center of gravity. But what if they are rotating in the opposite direction? The moments created by both of these would be opposite to each other and they will cancel if they are rotating on the same RPM. So that's the case when your drone would be stable. So in the configuration B, if you go, the drone would have a stable motion. But if you are going in the configuration A, which the configuration A will provide unstable motion. And we had a small video of this one that we tried. We tried during one of the competition, and you can see that how does this drone was trying to hover at the same, drone was rotating at the same location, and then it finally crashed. So yeah, that's what was the dynamics of the drone. But let's move forward and understand how do we control each thrust, yaw, roll, and pitch. So consider these 4 rotors: front left and front left, front right, rear left, rear right. So here the arrows indicate the motor torque direction. So you can see that these two are the counter rotating. Similarly, these two are the counter rotating. So we have to maintain this type of motion. So in order to control thrust, in order to control thrust, we actually give the motion, the same throttle to all the controller. And because of this thrust, your vehicle goes up and down. When we want to perform the rule, we will make the for example, if we want to perform the roll towards the right direction, we will increase the throttle on the left hand side, which will increase the lift towards the right hand side, and we will decrease the throttle towards the right side, which will actually tilt our vehicle towards right, and that's how we perform the roll. Similarly, in order to perform pitch, we will increase the pitch. In order to perform pitch down, we will increase the thrust on the rear rotors and decrease the thrust on the rear rotors. For performing the yaw on a diagonal one, on the diagonal rotors, we'll maintain the same thrust, and on the other one, other diagonal, we will decrease it. So this combination we have to maintain for performing drone motion. But now the question is, how do we take care of these motions or these combinations in a in algorithm on an algorithm level? So if we actually make the four cases of thrust, yaw, pitch, and roll control, we see this for all the four rotors. These should be either addition or subtraction. Means addition sign says that increase the throttle, subtraction sign says that decrease the throttle. So that's what brings together and make the motor mixer algorithm. So this combination that we see is a motor mixer algorithm, and we'll see the implement in one of the demos. Let's move forward and uh, understand more about controllers. But before that, let me ask you, are rotorcraft stable? Do you think rotorcrafts are stable or not? So I can see there are few new names in the room. So Vedant, Shiddat, Sharan, Shelly, Pushkar, Pritpan, Raj. What do you think? Drones are UAVs are stable or not? Especially the rotorcrafts. Are they stable or unstable? Let me know in the chat. Let's think from the very simple, very easy, very normal perspective of the stability. What is stability? If something deviates from its original position, it comes back to its origin. If it comes back to its original position, it's actually stable. If it doesn't, then it's unstable. So what do you think? Are the rotorcraft stable or not? Tanvi says rotorcrafts are stable. Okay. How many people agree with Tanvi? If no one is answering, I'm assuming that everyone disagree with Tanvi. Just let me know yes or no in the chat. Without your answers, I'm not moving forward. Uh, I need your participation in this session. So Shelly also says that these are actually stable. Manjri says no. Path says no. Mitan says yes. Good. I'm liking it. Anyone else? Anyone else? Arjun says in their innate nature they are unstable, but in the phase of flight where instability is less, we call them stable. But inherently they are stable. Okay. Let's find out if the drones are stable or not. So for the stability, the basic definition is if we move from its original location, does it come to its original position or not? So that's called the stability. So consider the case of yaw. So if you yaw your UAV, is there any mechanism or anything which brings back to its original position? If your UAV is in air, actually there is no motion that brings it back. Similarly, if we go for roll, pitch, or yaw, roll, pitch, or thrust, there's no, I'll say external factor or its inherent factor, moreover, its inherent factor which can actually bring it to its original orientation or position. And that's why drones are actually unstable. UAVs are unstable, especially rotorcrafts. Fixed wings are also UAVs. Fixed wing aircrafts can be stable. Fixed wing aircrafts are mostly stable. But the rotorcrafts, especially we are talking about like quadcopters, they are inherently unstable. So if they are unstable, how do they fly? And how do we witness such a stable flight? Although the drones are unstable or the your rotorcrafts are unstable, we can control them. And the controllability is actually gives us an opportunity to make them stable. So does it make sense that now that your UAVs are unstable, but they are controllable? So let's move forward and understand how can we actually control them. So let's set up a control problem and see that what all things are needed. So consider a case that we have to hover the quadcopter at a specified height. So you all would have learned about the closed loop controllers uh, uh, in your engineering program. So we'll take that simple case and see that how does it work. So consider our quadcopter started flying and uh, moved to a specified height, and it's actually we want to hover it here, maintain this height. So what is the simple controller is the can be the that we have the plant model. From plant model, we are calculating all the states, and these states are actually measured through these sensors, and these sensors are fed sensor information, especially the altitude is fed here, and we want to maintain it with the altitude HD. So the difference of both are fed to the controller, which gives the appropriate thrust command, which goes to the motor mixer algorithm, and which actually controls or maintain our UAV at a specified height. But let's consider a case, if this is a very simple case we are considering, let's consider a case where a gust came. Now, in the case of gust, what will happen? Will it stay at its original location? No, it will actually tilt. The gust can tilt it. And because of the tilt, it's actually now it's in a rolling motion. And because of rolling state, this will move to a new location. So now, if you see, it has moved to the new location. We need some mechanism to make it stable or make it to bring back to original position. We should have something which can actually bring it to its original location. So let's design a better controller for this. So consider we have this plant, sensors are connected. From sensors, along with the sensors, we have motor mixer algorithm and we have controller. And now not only roll, but yaw and pitch can also make a difference because of gust. So we want to try to maintain roll, pitch, and yaw as 0, and we want to maintain a reference altitude. In that case, we can actually take all these reference, and from sensor we will measure all the original state, all the current states, and accordingly we'll design a controller and feed to the motor mixer algorithm. So we have roll command, pitch command, yaw command, thrust command are fed into the motor mixer algorithm, and then our UV should be able to control at a specified altitude. Do you think we would be able to control it, or should we need any changes? Do you think if you think, okay, this will work, let me know it works. If it doesn't, just mention no. Be quick with your answers. Okay, let me help you to understand it with help of an animation, right? So we designed this controller and we are taking a position reference of this location. So now if a gust is coming, our rotorcraft got tilted. But as we set the roll, pitch, and U as 0, this will bring back to its original orientation. Although it bring back to the original orientation, we are not at the original position. So actually, we are hovering at, we maybe our rotorcraft is hovering at the same altitude where we wanted it, but we are not at the same location. So do we need any more modification here? let's move forward and see what do we need. If position reference is an error, so we need to design a flight controller which can actually take care of, along with your altitude, it can also take care of your position as well. So this architecture is what we had in the previous slide to keep your to maintain your roll reference, pitch reference, and your reference. Here we are putting estimated U instead of your reference. The estimated U is actually calculated from your position reference. So it's quite possible that in your environment, in whatever direction you want to move your drone, you always want it to point into that direction. For this purpose, we need to estimate U. This estimated U is nothing but from one coordinate to another coordinate when your drone is moving, which direction or which side of the drone is actually should be forward. So once your position reference is maintained from this position reference, we can actually, from our sensors, we can actually check the current position, and with reference position, the difference is actually fed to the inertial frame to the body frame. So uh, does anyone have a doubt here that why do we need an inertial frame to body frame, or everyone is clear that why do we use it? Or what is the inertial frame and body frame? In the previous session, we talked about the body frame, but what is the inertial frame? Sai, Ritesh, Pushkar, Path, Madhur, what do you think? Why do we need this inertial frame to body frame? If you want me to discuss, let me know in the chat. I'll do that. So your vehicle is actually flying in an inertial frame. So inertial frame is mostly considered attached to your earth, well, mostly what we call as a northeast and downwards or northeast upward frame, where we can consider that the center of that frame, reference of frame is frame of reference is actually located at your takeoff point. Now, from that location, we are actually estimated position of your vehicle. So your position is always relative and it is in inertial frame. But the controls which we are applying are actually in the body frame, because all of your rotors are fixed on your body frame, on your body of your quadcopter or your rotorcraft. So that's why we need to convert these position reference from inertial frame to body frame. And then we need to design the controller accordingly, which actually generates the roll reference and pitch reference. So this controller actually helps us to take care of our drone, to maintain it at a specified location. And that's what called as a position controller or outer loop controller. We also have this YPR controller, which is known as inner loop controller. And this inner loop controller is actually helps us to maintain the orientation of our vehicle. Along with that, we have this altitude reference, which is actually altitude controller, which takes care of maintaining the altitude of vehicle to the reference altitude. Now, all these controllers we talked about, these controllers are actually helping us to control our vehicle at the at the given at the given position and in the given orientation. Consider a case of an autonomous mission. In the autonomous mission, we have, say, few waypoints, waypoint 1, 2, 3, 4. We have the GPS coordinates of that. So we have some position, but how do we actually generate the command for this purpose? Or consider an obstacle avoidance mission. In the obstacle avoidance mission, how this position reference would be calculated? So where will we get this data? Any guesses? we have 25 people in the room other than me, and that's a good number for us to discuss the drone dynamics and controls. So if you can let me know that from where does the position reference or estimated your or altitude reference would be calculated? We can move to the next section. If you want to learn about it, just let me know yes. Else I can skip the next section. Om, Parth, Pushkar, Ritesh. Anyone? Any wild guesses? Okay. In case of the autonomous missions, these are actually generated by your guidance algorithms that you have. And the guidance algorithm is actually makes your vehicle gives your vehicle autonomous mission capabilities. So we will talk about this. How does this guidance algorithms are generated and how does it work? But let's move forward and see this demo that we package delivery demo that previously we discussed in our previous webinar. So let's go into the Simulink model and see this. How does actually this flight controller architecture that we discussed we just discussed in the slides is actually working is actually working. Allow me for a minute. I'm trying to open this model in Simulink. So this is the UAV package delivery example that we previously discussed. And this was our multi-rotor model, which has its own flight dynamics and along with the controller. So let's get into this multi-rotor model and see that uh, what all the controllers it has. So we see here in this section that some guidance logic is coming from the GCS and the flight computer, and this is going into the flight controller module. So let's go get into this inner loop and plant model and see that what all do we get. So instead of this, let me go to the high fidelity model. So you can see here that we have the position control, uh, velocity control, which is nothing but your throttle control and your attitude control. So this is your inner loop and these are your outer loop flight controllers that we were discussing in the slide tag. Now the idea is you have all these controllers are available here, but how do we actually implement these controllers and put on hardware, right? So for this one, so this is the controller that we were looking at the slides. So let me bring again here this architecture. Here we see three types of controller: position controller, yaw pitch roll controller, and altitude controller. So these three types of controller that we see here, you can notice here the position controller is there, which is outer loop controller, attitude controller, which is nothing but your YPR or inner loop controller is here. And then we have this yaw controller, which is estimated yaw control. So all of these are making your flight controller. And here you see that we have this control mixer, which is nothing but your motor mixer algorithm, the way we previously discussed. So it's take total thrust requirement, tau, yaw requirement, pitch requirement, roll requirement, and convert them into the required motor demand. So now, once we learn about these controllers, the idea is we have a lot of these controllers here. So let's count these: 1, 2, 3, 4, 5, 6, 7, 5, 6 controllers we have. Now, the best one, depending on your controller performance, you may need to tune it. And for this purpose, you can use Similink's auto tune capabilities. We are not going to get into the controller tuning capabilities in this session. But if you are interested to learn about these, you can. I'll share the links with you on the mail, so you can go through these and learn more about it. Now, as we have learned about the flight control architecture, let's move forward and understand that how does this flight control architecture that we modeled in Simulink actually gets integrated into your your flight controller hardware. So consider your flight control code or your flight computer code as a bigger code which has multiple small subsystems. It has sensors, battery management, Bluetooth USB connectivity, internal messaging, motor controller, payload drop, memory management, and something more. Now the idea is, how do we replace our flight controller model with these? And the idea, it's not just the one thing that goes replace. We can replace your controller module, your navigation module, and your guidance module, in especially in the PX4 autopilot with the PX4 support package for UAV toolbox. So the requirement for this is that whatever the command and sensors we are putting input should be actually come as an output, because this complete work as a function. So let's explore various ways of building the flight code. So there is one approach of building the flight code is you write your manual C code, compile it, and load it on hardware. So now think about this approach. Do you think there would be any issues with this approach, or this approach would be good enough? Think aloud about this one and let me know if you think there would be any problems. Let me just come. Any guesses? What do you think? What can be the problems with this approach? Before we go for the break, I want to show you how can you deploy the code to your flight controller code from Simulink. And for that purpose, we need to understand why do we need to go for that approach. In order to appreciate that approach, we should learn about what are the problems with the manual approach that we have. So if you are developing your flight controller code manually, what can be the consequences? Every year, your team gets the new students. What if previous year, if your team designed a flight controller code, and next year some other person is handling it? Do you think that it would be the same understanding, same understanding with the new developer, what the original author had? Mitan says no. Okay. Uh, Manjuria says also no. So think aloud about it. What can be the problems? first thing I feel is if I had to write a code, uh, I should have the skill of particular programming skill. Mitansh says the readability and reusability. Well said, Mitansh. These are obviously the two big things, the which actually which actually makes the model-based design uh, approach more useful in such scenarios, because model-based design approach uses it. In the previous session, we talked about the model-based design approach, where you'd actually develop your model first before generating or developing the controller. Uh, but let's get into more into this and see what can be the problems with the writing your manual C code. First problem is you should have a skilled person who has a skilled developer who has the particular programming skill. Second problem that I can think is uh, you should have, along with the skill, it would be a lot of effort writing the manual code. And as humans are writing it, obviously it may face some errors. So these are few of the issues, but the main issues, like if you consider the situation the of tuning the controllers. In the previous one, we saw that there was total 6 controllers. Even if you are going to use the PID controller, the 6 controllers that we are going to use, if you want to tune the performance of all these 6 controllers every time, going to your code, changing the parameters and deploying it on hardware, would it be an easier approach, or it will be a time-taking approach? I feel it would be a time-taking approach. Also, if you want to see the impact of some code on your vehicle performance, you may not be actually trace the issues that you have. So connecting the final effect with the code that is resulting in would be actually very difficult. So what is the solution? Do we have any solution for this? So second option for this is model-based design approach with Simulink. You design your flight controller in the Simulink, generate code. No need to write your own code, investing a lot of time in the developing your own manual code. Instead of developing that, instead of writing your manual code, generate this code and compile and load it on hardware. Now, with the Similink's model-based design capabilities, you can continuously monitor and tune its performance. So the controller performance we were talking about, actually you can change the parameters of that vehicle within the Simulink itself, and continuously you can see their effect. I'll be showing you a demo, how do we do that. But before that, let's move forward and see the small demo on the flight controller deployment to Pixoc hardware. I'll talk more about it. So right now I have this Pixoc flight control hardware is connected with me here. We'll talk about various options that in the Simulink is available for this purpose. But before this, let's see this simple demo. Here you can see that we have developed already a controller in the Simulink, which has the position and attitude controller. You have to open the model settings from modeling tab and select the appropriate hardware board. For using these hardwares, you should have the PX4 toolbox support package available. And you can see that all the PX4 supported hardwares are mentioned. So this demo I recorded for the PX4 Cube Orange Plus. So we have selected the PX4 Cube Orange Plus hardware here. And we have to also set up for HITL mode and Mavlink connectivity if these are required. So in this demo, HITL was required and simulator was required as Simulink, and we wanted to check on Mavlink as well. And as we want to see the generated code, so we are actually selecting these options to generate the report. Once you go for these ones, you can simply go for your hardware tab and you have to select from here. You can see the hardware board is PX4 Cube Orange, and we have to run the code on hardware. So we'll use run on board method, which is actually an external mode. Once you select this, you will see that the two options comes. One option is monitor and tune. So monitor and tune option actually allows you to make the changes in the design and continuously see their effects. Second one is build, deploy, and start, where you actually generate the complete code and deploy it on hardware. And that's the phase when once you finally have the code completed, you do it. So let me go back a little back and show you like how does this uh, code generation starting. So we see here, okay, we see here that monitor and tune, along with the monitor and tune, we have this build, deploy, and start feature is available. So let's go for build, deploy, and start feature and see. You can see at the bottom that this code started generating and compiling. Code generation started. Now, this generated code will be actually deployed on hardware. Also, the code we generate, we see a report for this. So you can see that for complete a code that is going to be on flight controller, we have various C files available for this, along with their data files, utility files, and model files. Everything is available here. And this comes with the various reports for the code performance that is also available here. So this can actually help the teams like you to design their own controllers and generate the code and deploy directly on the hardware. Do you think this can be useful for for your team? If you think this is useful, let me know in the chat. Say yes or no, guys. Is it useful or not? Okay, so if you guys feel it useful, let me show you something more with the PX4 firmware. But as we have learned about why the flight, in this section, we learned about what is the flight controller, why do we need a flight controller, where does it fit in the bigger frame of the simulation, hardware in the loop simulation. Before we move forward, uh, there is another question for you guys. You may not need to answer it, but do you also have this doubt that where does this overall sim code that we are generating from the Simulink is actually getting integrated with the PX4 firmware, existing firmware? If you have this doubt, let me know yes. If you don't have, if our slide answered it, say no. I want all of you to learn something uh, in a deeper way so that when you are using any software, you know why are you using it. If you don't know, uh, it's not just about pressing the one button after another. You should actually know that the button you are pressing, why are we pressing? What is the concept behind each one? And that's why we need to understand that why the PX4 toolbox, why the PX4 firmware and the Simulink based code get integrated. So let me bring this simple architecture share a simple architecture with you. I hope this picture is visible to all of you. Let me know, yes or no. Is it visible, guys? Can you confirm in the chat? Okay, so this is the PX4 firmware architecture. So now if you look for here, they have the way we discussed in the or one of the slide that it has various sub components in the architecture. It has some storage based information. It has various drivers to use your camera, GPS, RS input, and your IMU drivers. Then for external connectivity, Mavlink and UDP protocol, it has few more subcomponents. And then finally, the flight controller is there, which has your navigator module, your position controller, your attitude and rate controller. So all these are available here. So now the idea is we are actually talking about this autonomous flight controller, position controller. We just replacing these code with Simulink model. But how do we integrate it? And are there any ways that we can get the sensor information from our autopilot directly? Because if you want to perform a simulation and I want to connect my hardware, so think a situation you developed a Simulink algorithm, you developed your controller algorithm in Simulink and you deployed on this flight controller hardware, right? Now, how can we actually put it on the hardware and test it, because I want to put my flight controller hardware code here and want to test how adequate my controller algorithm works in a real scenario, or even in a simulated scenario before we go for the physical flights. So for this flight controller architecture, the PX4 best toolbox support package offer various various blocks that actually helps us for this purpose. So for storage, from the storage system, we can directly use this read parameter section and read the information. All the messages, especially from the sensor, these are coming. We do have the PX4 URB read, URB write messages that we can use and read and write information from the PX4 hardware. We can also get the information directly from all the sensors. So from sensor hub, you can actually get your vehicle altitude, accelerometer, gyroscope, magnetometer. And you can also connect your RC controller transmitter here and put your RC controller input directly to your PX4 hardware. So this actually gives the opportunity to make your simulation more and more realistic and interact in the environment. So now, are you interested to see a quick demo in Simulink where we will read some information from the PX4 supported hardware? So I have this PX4 supported hardware. Let me bring this closer. Do you see some light is blinking here? Or let me just change my camera view so that it would be easier for you to see. Okay, do you see the light is going? Let me remove this. You don't see any light here. Now, let me connect this. Okay. Are you guys interested to see the small demo before we go for a break? Mitan says yes. Anyone else want to see the demo? Just Mitansh. Okay, Tanvi, Madhur, Jenna, good. So we are going to have a small demo in the Simulink. So what are we going to do is we are going to read the gravitational acceleration parameters from this hardware. So in the last demo, we discussed that how in the Simulink library browser works. So here we go for the library browser, and in the library browser is actually the library for all the toolbox related or support package related capabilities, or the functions that are available in the form of blocks are available here. So let me go for the PX4 support toolbox support package here quickly for you. There is the UV toolbox. Let me search PX4. Looks like some issue at my end. Okay, we can see now there are a lot of library. The PX4 UAV toolbox support package has come up. Let me just zoom it for you guys. So we see here that for the PX4 UAV toolbox support package, we have a lot of blocks are here. So you can see this peripheral blocks, sensor blocks, and URB read and write blocks. So what are we going to do here is we are actually going to we are going to actually read some sensor data from here. So I'm bringing this drag and drop the sensor acceleration URB read block here. And let's click on this block and we see that there are various topics we can subscribe to. So right now, sensor acceleration is selected, but you can go here and actually can select various messages from the PX4 firmware. So you can see that action request, actuator armed, actuator control, actuator outputs, airspeed, actuator test, airspeed validated, airspeed wind. there are some more features, some more messages are available. These messages are nothing but your continuous sensor information. These are fed here. So let me put this. So here we can see all of these are informations are available. So let me select simply the sensor information. Where is my sensor in? Sensor data is available. Sensor acceleration dot message. So we select this sensor acceleration dot message, and let me connect the first block, because the sensor are going to be in the there are sensor information are going to be in the 3 sections. So we will take the bus selector here. Let me put the terminator. And let me push this sensor information here, X, Y, and Z, the signals we want to connect. Good enough. Okay. Now we have created the Simulink model. We are just going to read one message. Now, before I connect my PX4 controller to the hardware, to the system, let me show you my device manager and show you the difference that comes here so that we can validate that our drone is connected. Sorry, our PX4 is connected. So right now, if you look at here, you can see that there are in the ports, there are only 3 devices are there. So COM3, COM7, COM8 are busy. Now my PX4 flight controller is free. Let me connect this. We see a light here, and let me just update this. Okay. Now if you see here, you can see that USB serial device COM10 has come. Although it does not rename as a your QPilot flight controller, which can be actually renamed, but USB serial device at COM10 over hardware is there. Now, once we fix this, now our USB flight controller is connected. It's time to actually configure the Simulink model and set up the flight controller. So I'm going to the model settings, and in the model settings, I'm going to directly for the hardware implementation, and I'm going to select Pixop Cube Orange Plus here. And along with this, the device details, advanced parameters, these are good enough. Let me apply it. Target hardware resources. I'm going to turn off HITL mode and Mavlink as well, because in this demo, we don't want the Mavlink connectivity and we want to read the messages. And let me put this timing as infinite till I want to control. Now we want to run the information from the hardware. So I'm going to do the run on board. And here we are going to do the monitor and tune and see if we get the results. So you can see here for this Simulink model, the code generation started, code generation templates completed. So the code generation templates that we are talking here is nothing but for a hardware, the specified code generation templates are there, and going with this code generation templates actually helps to optimize your code's performance for the particular given hardware. Let me just make it bigger again. And this is game that disconnect the PX4 autopilot from the host computer. Click OK on this dialog box. And this is just we are going to do. At the bottom, we can see that code generation has templates is completed. This first time this simulation setup takes a little bit time, but once your Simulink model is set up and your code generation templates are ready, it becomes quicker. So now it's showing that's connecting to PX4 Cube Orange Plus. I'm keeping this in this position, and let's see that how my acceleration values comes up. So this is now initialization game. Okay, now you see here that for the X, it's coming as 9.868. So this is nothing but your gravitational acceleration value. Now, from this mode, you see it's 9.8. What will happen if I tilt it? Do you see any changes? Let me know what change do you see in the acceleration information. Mitanj, what change do you see in the gravitational acceleration? Why there is so much change? Because my hand is not steady, and along with that, it also takes the magnetic interference from surroundings. So if you see this, the gravitational acceleration has went to the Z direction because Z is acting this way. Now, if I want to make it, if I tilt it, you'll see that the gravitational acceleration went negative, right? So right now the gravitational acceleration in Z. Let me do another one, and you see this how my gravitational acceleration shifted to Y. Right? Let me make it positive now. Now you see that gravitational acceleration become positive. So that's how we can actually read the sensor data from Simulink model to hardware, Simulink from or hardware to Simulink model. And that is possible only when we can interact with the PX4 firmware. The image that we were looking at earlier for the PX4 firmware, you can see here that all these blocks, PX4 URB read, URB write, URB messages, radio control transmitter, these all are the part of PX4 toolbox support package. And the same we can observe here as well. So let me go back to the Simulink model and show you the other things. So like this is the bigger Simulink library browser I have. And let me find my UV toolbox support package for my bad. So you can see that PX4 peripheral blocks, URB read and write blocks, utility blocks, everything is there. So if I go the read and write blocks we use, there are various sensor blocks, GPS, magnetometer, gyroscope, accelerometer, directly to fetch this information of sensors and develop your flight controller algorithm. So these are some of the Simulink capabilities that you can use, and some of the PX4 support package capabilities that you can use to design your flight controller and perform the simulation. So now we'll move forward and discuss about various other sections that how can you perform the HITL simulation and how does it work. But these are few of the hardware. A few of the hardwares are supported by the PX4 hardware support package for UAV toolbox. So if you are going to use any of these hardwares, you can directly generate the optimized flight controller code and deploy it on your hardware. But if you're using any other flight controller hardware, please feel free to reach out to us and we will help you to generate the custom code for these other flight control hardwares as well. So now, do you think this flight controller modeling and simulation becomes easier with the Simulink? So which teams would be there, who would like to try this? Mention your team name if you feel that your team should use it. Maybe your institution name would be the best to know. Any team? Tanvi, Shelly, Path, do you think this will help you guys? Okay, good. So in this section, we talked about how can we model the flight controller in Simulink and what is the basics of developing a flight controller, why do we need it, and how do you model and how do you deploy it on hardware. So we saw two features here in the Simulink. One was the monitor and tune feature. When you are using monitor and tune feature, you can actually work on tunable parameters and deploy it. And the build, deploy, and start is actually used when you finally want to deploy the final flight controller code, which is actually optimized and you want to go for flight test. So in that case, you use the build, deploy, and start. In that case, you don't have the access to the tunable parameters. So now with this understanding, we'll move to the next section and we'll talk about the setting up ground control station for HITL simulations. But before that, we have already completed around 80 minutes. So let's take a quick 5-minute breaks and meet again at 6:25. Does that sound good, guys? Okay, I'm putting a timer here so that you guys can come back on time. Hello, everyone. Hope you're back. If you're back with some more energy, had some drink or something, and if you recharged, just let me know in chat that you are there. Who all are back? Just Mitansh is back. No one else? Yeah, 2 minutes over. G has raised the hand. Jenna has raised the hand. Okay, Jenna is here. Mitansh is here. What about, oh, Om is here. What about Anushri, Anushka, Aryan, Fireflies, Madhur? Are you guys back? Okay, good. Good enough. I hope you guys had some time to refresh. I also got my coffee. And here for the next section. But before we go for the next section, uh, again a small question for you. What are you expecting now? That we learned about flight controller, we learned about drone dynamics, but what should we be able to learn in the next 30 to 40 minutes? What you should be able to achieve in this? You have a drone, you have this autonomous UAV competition. What are your expectation that next 30 minutes, what should we be able to achieve? Do you want to learn about flight computers? Do you want to learn about smart drone algorithms? Okay, I think that become a bigger question. So how many people are interested to learn about flight computers? Type FC if you are interested to learn about flight computers. We just learned about flight controllers. Mitansh is interested. Mitansh is consistent. Jenna is interested. Madhur is interested. Anyone else? Okay, good. So if we have a good people who wants to learn about flight computer, and before we get into the comparison of flight controller and flight computer, let's have a small let's move forward and see that once you deployed this code from the PX4 to the PX4 hardware, how does it get integrated? And if your flight controller algorithm or code is now on your hardware, how do you actually make this setup and everything work? So in this case of autonomous mission, you should set up a ground control station. So for setting up ground control station with your hardware, there are some straightforward steps, and we will share the links with you for the setting up your PX4 in HITL mode. So if you are not aware, the HITL mode is stands for hardware in the loop simulation, when your hardware actually comes in the picture. So here our hardware is the flight controller. And for this purpose, how do you set your airframe in the ground control station? How do you set up your mission? Everything has a detailed steps, and this web page is available. I'll share the link with you after the session in the documentation along with the slide deck where you can refer more. But now consider your ground control station is set up and your PX4 hardware is also set up. And in the previous session, we also talked about how can you do the scenario simulation, right? And we also talked about how can you do the flight modeling. So let's see in this small demo that how does it work. So for this one, assume that we have different MATLAB sessions are running, and each MATLAB session has single Simulink model. Now you would be interested to know why are we running multiple MATLAB models? So consider this in this way that instead of running everything in a one environment, your simulation, which is actually just the visualization, you are running at a different platform, and but you are using MATLAB for this purpose. You don't have your drone or your rotorcraft, but you are using Simulink or MATLAB and Simulink to visualize, to model this flight dynamics. But that is again in the different MATLAB. So you have a MATLAB 1, MATLAB 2 session here. And similarly, you have flight controller hardware is installed on it. So let's see how do we do it and how do we implement actually the Mavlink protocol here. So in the in the first slide, when we were talking about setting up this environment, we talked about Mavlink Bridge Source and Mavlink Bridge Sync. So let's see them in the visualization here, that how does it work. So this is actually the simple PX4 flight visualization model, where you can see that 3D simulation environment and simulation 3D vehicle has been set up, this which is nothing but your rotorcraft. And whatever the data from this simulation is, whatever the view in the simulation our camera sees, we can actually feed it if we need it for our flight computer purpose. But the idea here is, in the PX4 environment, we have to, for the simulation purpose, for visualization purpose, we have to get the vehicle's position and its orientation, which is attitude, from the PX4 firmware, PX4 hardware, right? Or your autopilot hardware. So your autopilot is connected to your system via the local host port, given this port. So we create the Simulink model and create a UDP protocol connection via MAVLink on the UDP port 25,000. And here another Simulink model is there. So here we are creating a Mavlink bridge source. So this is the actually address of in the Mavlink bridge source for the UDP 127.0.01 and remote port number. So with this information, we get this and we add another port here with this 25,000 remote port, so that these informations are shared from here to there. Now, when we are running the visualization model, you'll see that our visualization model has started taking the information from the PX4 flight controller. But our PX4 flight controller is connected, flight code is running, but there is no UAV dynamics is working yet. So we have to run the UAV dynamics separately. So consider this. This is your flight controller, but you don't have UAV, and your UAV is in a simulated environment in the form of the digital twin or UAV dynamics. So this is your UAV dynamics Simulink model. So when we run this UAV dynamics Simulink model, you can actually fly this mission. So in the Q ground control, you set up this mission and you can fly easily this mission. You may see some lag here. The reason for this, when you are running the multiple MATLAB sessions and the system actually and the system is doing simulation on all these various MATLAB sessions, there would be a time lag of receiving and sending the information. And because of this time lag, you can see that the visualization may not be very smooth. But if you are going for the higher hardware, better system, then it is possible. But I'll suggest, instead of going for a higher system configuration, what you can do is you can run this on multiple computer systems. So here, if we go back and we see this, when we were creating the UDP protocol and Mavlink bridge, we have this information of this remote address. So connect your all the systems that you want to run MATLAB session using same network, and on the same network, you replace this address. So with this address replacement, you can actually send the information from run one MATLAB system running in one laptop to the another laptop or another computer system. And you can make this simulation faster. I recorded this simulation on my single system, and that's how we see that everything is working here. But it becomes quite easier if you are using multiple system and you're working as a team. And this demo comes as an example. So if you want to learn more about this demo is available here. I'll share the link with you guys for this. So this big demo is available, where the obstacle avoidance with Jetson with PX4 autopilot and the hardware in the loop simulation is available. And for this demo, this complete architecture, how does it work? How does it your Pixel works and NVIDIA Jetson or your Raspberry Pi that you will replace with Jetson? How does it work? Various sessions of UAV dynamics, your flight controller which deployed on the autopilot, your scenario visualization, how does all of these works is actually coming here in the picture. So I'll share this link of this one in the chat so that you guys can have a look, and feel free to let me know if you guys have any doubt. So if you guys have any doubt when you are running this demo, you can always reach out to me or our team at roboticsarena@mathworks.com. So I'm sharing the email ID with you in the chat. Please feel free to ask me questions or doubts if you have. These are the big demos, which if we run in the MATLAB, it will take time. So we have recorded these demos and kept it here. Now let's move forward and learn about the next thing, which is the code generation and deployment to flight computers. So before I go for the flight computers, talking about what the flight computers and why do we require, let me know in the chat what flight computer hardware your team is using. Are you using Raspberry Pi or are you using Jetson board? Are you using Raspberry Pi? Manjari is using Jetson. Any other team? Jenna is using Jetson. So Jetson with Raspberry Pi is now on 2-on-1. Home is again using Jetson 3-on-1. Raspberry Pi 3-2-2. So now the new Raspberry Pi and Jetson both has a GPU platform, GPUs. So depending on your capabilities and requirements, which one you are using, you can use the flight computer hardware, based on your choice. But now the idea of our next section is to use the same demo, but extending it for obstacle avoidance. Last time the demo what we saw for was just for the waypoint follower, where our UAV flew from point A to point B. But now, how do we capture the visual, capture the images from the camera which is located on our UAV, and how do we filter them and create some create some decision scenario or decision metrics from where we can actually find if our UAV needs to avoid the obstacle or it need to go straight. If it is avoiding obstacle, it has to plan its way. So we'll talk about this in this session. So in the previous one, we talked about uh, our architecture, how does it work with the with Pixoc flight controller. But now, when we want to perform the mission which requires the higher guidance and higher autonomy algorithms, that's where we need the flight computers. And these flight computers are used as mostly in the competitions, student competition, they use the Jetson GPUs and Raspberry Pis. These are used flight computers. Can anyone let me know in the chat or on the mic that what is the difference between a flight computer and a flight controller? What is a flight computer and flight computer? Because first time when someone asked me, my doubt was, aren't they both the same? And if they both are not the same, how are they different? And do we really need both? Because if I can deploy the flight controller hardware to Pixoc Autopilot and Raspberry Pi and GPU has a better space, better memory, better performance, why don't we simply just deploy both the codes there? How many of you have similar doubts? No one has? Great. This time marathon teams are really doing great. If you are really clear about if they are same or if they are different. Okay, how many people think they are same? If you think it's same and we just need one, just mention one. If you think we need both, mention both. One or both. We have seen that few of you are mentioned Raspberry Pi and Jetson, and I believe you would be using the autopilot controller. But if you have doubt that, if you have the same doubt, mention in the chat doubt, so that I'll let you know that how are they different. Manjari is saying they are using both and they need both. But do you have a doubt how they are different? Computer is used to process different things such as camera feeds, run models, etc. Flight controller integrates the sensor and works as the stability naturally. You are correct, Madhur. Madhur. So Madhur is saying that computer and the flight controller both are different. Controller takes care of stability, and your flight controller hardware comes with multiple sensors. Sensors like your IMU sensor, your uh, accelerometer sensors, magnetometer sensor, and they actually helps you to stabilize your vehicle motion. But when you want to perform high autonomy missions or smarter missions like obstacle avoidance, or if you want to follow a particular object in the environment, all or in all such cases, you need the flight computer, which has the particular perception algorithm for that. And for all these purpose, we go for the flight computer. So yes, they are different. So now again a question. We have this flight controller and computer, right? So if this was our architecture that flight control software architecture we were looking for earlier, and we saw that this is our controller algorithm is coming and we are getting some guidance. So now this guidance we are understanding is the actually generating all the commands. So if I minimize it, this comes like this. That's controller is actually stabilizing the system against perturbations, whereas the guidance is actually guiding the system for next action to follow the mission. It also calculates the required next move based on the purpose of object identification, tracking, or maybe taking some corrective action for that. So now, depending on this, what do you think? Where does the two hardwares will go? So Pixoc flight controller actually takes care of your controller algorithm from sensor information, whatever we get, and the flight computer actually takes care of your guidance algorithm. So now the idea is, if these guidance in flight control software architecture where we look for that, this guidance and controller works together, and we need to develop these position reference and estimate radio and altitude reference commands. In these cases, the codes which are actually running on these two hardwares need to be integrated and tested together. They both should have some information transfer way among them. And especially in the case of hardware, you may be able to connect some particular hardware connectivity ports and you would be able to share this information. But in the simulated environment, how do you do it? So, okay, the small quiz. If you need to track some objects during the mission, where will you deploy the object tracking algorithm? It will go on a flight computer or flight controller. Just mention computer or controller in the chat. Is it flight computer or flight controller? Where your object tracking algorithm will go? Okay, most of you are saying it will go on the computer algorithm. Uh, Let me ask you another question. If you are working on a mission which does not need all of these and just need you guys to follow the waypoint mission, where the waypoint mission uh, algorithm will go? It will go on computer or controller. No obstacle, nothing. You are in a clear environment and you have to just follow the waypoints. Flight computer or flight controller. You can use ground control station. With this understanding, think about for waypoint mission, where we just have the GPS coordinates and sensor information that where our vehicle is currently located, where this information will go. It go on a controller or computer? Arvind, Anushka, Aryan, Janki, Parth, Tanvi. What do you think, guys? Where does this algorithm will go? Parth is saying computer. Anyone else who says the computer? Okay. So Parth, you can do it with computer, but Shelly is saying controller. So Shelly, how do you really think controller would be good enough for that? So we have 1 and 1 on the 101 computer versus controller for a waypoint mission. I believe like some of you would be thinking about the same because we need the guidance, and guidance algorithm goes on the flight computer. Some of you would be thinking the flight controller because we have ground control station. But please understand that your flight controller also has adequate information and memory to perform simple missions such as waypoint mission. So you can perform waypoint mission even without computer, but it solely depends on what is your waypoint algorithm, and if it is a simple algorithm which has, and what is your hardware. If your hardware is adequate enough to control it, with the help of ground control station, you can do it. So in the ground control station itself, you can mention the waypoint mission. No need to put your waypoint mission in the flight controller. So the answer is you may not need both if you have the ground control station, not even the controller and not even the computer to deploy the waypoint algorithm. You just need to mention the waypoints in the ground control station and your ground control station will take care. So these are the few of the nitty-gritties we should understand before we develop our algorithms and put it on hardware. Now, with this understanding, let's move forward and understand for flight computers how the code generation and deployment works. So for the uh, for the NVIDIA Jetson, we have uh, there are various purposes for which you can use the uh, Jetson support package to develop and deploy your controller, where you have the lidar sensor, or you are actually putting up the heavy algorithms on the flight computers. For all these purposes, you can do the CUDA code generation and deploy it on hardware. So, for example, if you need to identify some objects, like is it a red buoy or yellow buoy or some other missions where like you are working in a closed environment where a lot of obstacles are there and you need to do your own path planning. All such things you can work with your NVIDIA Jetson, and for these purposes you can generate your CUDA node and deploy on your hardware. So with MATLAB and Simulink, it becomes faster to compute. You can develop directly your CUDA code. The way we have the C code in the C code for the flight controller, here you use CUDA code, and you can deploy it as exe static dynamic library and also interface with middleware. So all these capabilities are available and you can use. So in the last simulation model, we saw that we had the flight visualization in the Unreal Engine based Sim 3D environment, and we had the flight dynamics again in the Simulink. Now consider the same model, but in visualization, but think that we are actually gathering the information by the camera, which is located on our hardware. So we gather this information from the camera. All the pictures are collected from here and stream the data to the Jetson. So right now I don't have a Jetson hardware here, but you can connect the Jetson hardware the same way we connected the Pixoc flight controller hardware. So in the same way, same setup, you can actually collect this information and stream the information from the Jetson to the stream the information from flight visualization to Jetson. So you can see these images. This this is our simulated environment where my drone is there, and the images it is going to see, the camera is going to see, will be coming in the video viewer one. So we see this video viewer one shows that what environment my camera is looking for. Camera is actually having the view. Now the next one is we have to run this flight dynamics algorithm, flight dynamics, and we have to run this on we have to also run our onboard algorithm for Jetson. So for obstacle avoidance, whatever is our algorithm, we need to deploy it on hardware. So here you can see that from NVIDIA Jetson, we are collecting the images, and uh, in the video where it is all the images are coming here. So here in the same way, we have to go to the model settings and select appropriate hardware. So here you can see that hardware board is selected as NVIDIA Jetson. There are other hardwares are also available. And then you have to mention all of your uh, credentials, like what is your username and password. Once you do that, you would be good to go for this. Here we are using monitor and tune instead of build deploy and start, because continuously the pictures are monitored and the algorithm is running on hardware, but we are sharing the information from hardware to the Simulink Simulink, and we are making this complete HITL simulation setup work. So now here the video viewer 1 shows what my camera is looking for, and video viewer 2 is going to show us the information which is actually received there. Now here we come to the stream data to the Jetson, and we see this information is actually passed in a particular image format. So that we have to make sure that always the data stream that we are sharing should be the same. Now you can see that ports are the same for both of them, and make sure the compression and port numbers are same in the UDP and UDP send and receive communication. So once you make that sure, we are good to perform the data transfer between Jetson and the simulated environment. Now Jetson process all these information, and this video viewer information that you see here is actually converts it into a binary environment where our obstacle avoidance algorithm is actually can take the decision that black one are our obstacles and white one is the free environment. And that's how you can actually deploy your flight computer algorithm on the hardware. I'm pretty sure you all would be interested in the learning that how do you develop your obstacle avoidance algorithm. But this is not the session we are going to talk about these algorithm perception. In the next session, where my colleague Shovik is going to discuss about the making the smarter drone algorithms, he will show that what are the various resources are available, and what are the various capabilities are available which you can use to develop your algorithm. But I have shared the link of this demo in the chat where you can go and learn more about it. And once you do this, this is finally how do you simulate. You can see that with the ground control station, this information comes up and we finally can perform a mission. So here is my camera view, and this is the Jetson processed view, which is actually helping us to make decision, and it's avoiding all the obstacles. You can see that it's avoid the tree very closely, and it's land back. So with this, let's move forward and see. So scene view by camera in simulation and depth information derived on flight computer Jetson. I know you would like to know more about it, that what are the algorithms, how can you implement it on Jetson. So these video series are available where you can go and learn more about how can you use the GPU coder to prototype and deploy on NVIDIA driver, NVIDIA Jetson hardware, and how can you deploy the YOLO algorithms or deep learning algorithms on the hardware, on the Jetson hardware. We talked about the Jetson in this example, but don't worry about it. Similar to the Jetson, we have the support package for Raspberry Pi as well. And we are supporting the packages up to the Raspberry Pi 3 to 5 version. All the libraries of MATLAB functions are available to interface with the Pi along with the Simulink, and standalone execution is also available. These videos are available where you can learn more about how can you program your Raspberry Pi and Raspberry Pi using MATLAB and Simulink. We will share all these links with you in the session. With this, we can conclude that in this session, we learned about how do we complete this complete HITL flight simulation? In the previous session, we talked about scenario simulation and plant modeling. In today's session, we started the session with the understanding the drone dynamics. Why do we need the flight controller? And how do you deploy the code to the flight controller? Moving forward, we talked about how do you make these sources. So please read it as Mavlink Bridge Sync. So how do you connect these, how do you prepare this Mavlink Bridge source and sync, and how do you pass the information among them? And finally, how does the ground control station shares this information, and autonomy algorithm goes on Jetson, and this complete environment works. So the benefit of this bringing these hardwares and simulated environment is, consider your simulated environment of your Aerothon competition, which you are going to face in the November month. You can actually simulate complete mission here with your hardware before you make your physical flights. Capture all the images and use it to train your algorithm to make it smarter and smarter with synthetic data generation approach. With this synthetic data generation approach, you can develop your with the synthetic data generation approach and your actual images captured by the physical images captured by the by flying your drones in the flight test, you can increase the accuracy and precision of your algorithms. And that's where we come to the end of these sessions. We have few learning resources, but a quick recap, what we have and what we should use and why. So you should use UV Toolbox support package for PX4 Autopilot, especially to generate and deploy code to PX4 Autopilot hardware. We also talked about various hardware which are used for this purpose. Using MATLAB support package and Simulink support package for Raspberry Pi hardware, you can generate and deploy code for the Raspberry Pi. Similarly, GPU coder is available for CUDA code generation for Jetson hardware. These are the hardwares here. These are the support packages you can use and work around. And if you are new to the MATLAB and Simulink, we have this MATLAB and Simulink on-ramp courses are available. You can go through them and learn in detail. Even for the courses like even the fields like machine learning and deep learning on-ramps are also available to start your journey specifically in these fields. We have the dedicated learning resources at this page where you can apply for your Aerothon team license for the MATLAB and Simulink, and you can always reach out to us uh, if you need any support. And it also mentions a lot of video content here on these pages so that you can learn directly from these one. And the tutorial videos are available on the topics on the computer vision, robotics, aerospace, code generation, physical modeling to learn more about it. And yeah, I'll highly suggest you to go through this code generation training when you are going through this. This training is freely available. Is a It's a video series of it's a series of 5 videos that you can go and learn more about it. Uh, then we have for especially curated for the student community, we have 50 plus videos on our page. These aerospace and robotics videos are especially dedicated to the student competition teams like you. And we have the Facebook group, which has on the robotics arena, and the racing launch, which has around 20,000 plus members. Please feel free to join these groups. And if you have any doubts related to implementation of these, please feel free to reach directly to me or on the robotics arena at methods.com. That's all I have. I'm open to questions if you have any. Please feel free to turn on your unmute yourself and ask question. And if you don't have question, I have a question for you guys. Do you think this webinar could help you to understand how can you generate and deploy code on flight computer and flight controller and bring them together and perform the hardware in the loop simulation? If it helped, let me know in the chat. And if you have any doubt, feel free to unmute. Suman, we can stop recording, please.